My name's Dylan Beattie, and the first computer that I ever had was one of these. This was an Amstrad 6128. I was living in Zimbabwe. It was about 1987, and the Amstrad 6128 was not a very good computer. And it was a lot of fun. It came with a couple of games, like a little fighter pilot simulation game and a chess game that I managed to beat when I was 7. But the thing that made this computer really compelling to me is it came with a programming language called Logo, Digital Research Logo, which is what you saw in the introductory sequence at the beginning there. And the thing about Logo that I loved is I could use Logo to make the computer draw pictures and, create images, get things on that screen that maybe nobody had ever seen on any computer screen before. And, the Logo Programmer's Manual wasn't written for 7, 8, 9-year-old kids. So I would sit there trying things out, learning it, seeing what worked. And then when I made something work, I got this buzz. I got this thrill of I made the computer do what I wanted it to do. And for me, that thrill has never gone away. Throughout my entire career, probably still, a couple of times a week, I'll have that moment of, victory, that feedback loop in my brain. I made the computer do the thing that I wanted it to do. Now, this conference has got a whole bunch of people who are talking about all kinds of important things, quality testing, continuous delivery, performance, optimization, all these kinds of things, stuff that is useful, stuff that will help us solve real-world problems. I'm not going to talk to you about any of that stuff. I'm here to talk to you about art. And art, as Oscar Wilde famously said, is quite useless. So if you want to learn anything useful, maybe go and see a different talk. I don't mind. Or stick around, because maybe art isn't quite useless after all. There's another quote that I quite like to use in this talk. It's from one of my favorite authors, Douglas Adams. He says, "The function of art is to hold a mirror up to nature." Now, if we want to do this, first we have to invent the mirror. And that's where science and technology and engineering come into play. Because for centuries, we human beings have created machines that let us see the world around us in different ways and try and understand the world and the universe that we live in. We have created microscopes that have revealed this astonishing, beautiful world that has been hidden right under our eyes for since the dawn of time. And we've been able, thanks to microscopes, to take photographs like this. This is scales growing around the eyelid of a beetle through a scanning electron microscope. This is salt crystals growing in a dish of soy sauce. This is the spiral stems inside the stem of a banana leaf. Nobody had ever seen these until we created microscopes that let us take photographs of them. And we've sent cameras and satellites and people into space and looked back and seen our world, our planet Earth, from a whole new perspective. We've looked back on Earth from the surface of the moon. We've taken photographs from beyond the rings of Saturn, with our Earth, our pale blue dot, just visible down in the corner of the picture there. We've taken photographs like this. The pillars of creation in the Eagle Nebula, 6,000 light years away from Earth. Literally a factory where stars are born that we have photographed using our ingenuity, using satellites and telescopes and technology. And within the last few decades, we've used machines, we've used computers and software to start exploring another world that's hidden right under our noses, a world nobody had ever seen until we developed the technology to let us peer and start looking and seeing inside it, a world of mathematics and information. Throughout the 1970s, a journalist called Martin Gardner wrote a monthly column for Scientific American magazine, where he talked about mathematics, games and puzzles and numbers. And probably the most influential column that he ever wrote was this one from October 1970, where he described something called Conway's Game of Life. Now, Conway's Game of Life, as games go, it doesn't look like a particularly interesting game. It is a game played on an infinite board, an infinite grid, with only one player, and it has 4 rules, the rules of life. The first rule of Conway's Game of Life: all of the cells on this grid can be living or dead. If a cell has 0 or 1 living neighbors, it dies of loneliness. If a cell has exactly 2 neighbors, it survives for another generation. If a cell has 4 or more neighbors, it dies of overcrowding. And finally, the slightly spooky bit: if a cell has exactly 3 living neighbors, it comes back to life in the next generation of the game. That's it. That is those 4 rules describe everything you need to know about Conway's Game of Life. Now, in 1970, when this was first published, people used pencils and diagrams and graph paper to try and understand the behavior of these systems. And they drew diagrams like this. Now, these 5 shapes you may recognize. These are the pentominoes, the Tetris shapes, if you like. And you can see on this diagram the way that those shapes evolve over a couple of generations. But, you know, to me, looking at this kind of diagram, it's like going to a museum and you see the butterflies there that are pinned up in those glass cases. You can sort of study their behavior, but you don't really understand it. You don't know what's going on. And it wasn't until we started using computers to animate the Game of Life that we really understood the behavior that came out of these 4 rules. Let's take a look at those 5 pentomino shapes, but this time, instead of drawing them on paper, we're going to animate them. And watch what happens. Most of them stabilize very, very quickly, but this one over here, this goes into this infinitely looping, repeating pattern. These 4 little zigzag crisscross shapes, we call those traffic lights. Now, one of the earliest questions was, is the Game of Life finite, or are there patterns that can grow forever? The early 1970s, there was a team working with the computer scientist Bill Gosper, who discovered the first instance of what we call gliders. A glider is a shape that just keeps repeating, and every 5 or 8 or 10 generations it moves, translates itself across the grid, and it keeps going infinitely. There was another question: will these patterns grow? Can we build Game of Life patterns that continue to grow? Now, the glider was just one example of a whole category of what we call spaceships. These amazing, extraordinary shapes that glide across this infinite grid, all powered by these 4 simple rules. We've got gliders, we've got spaceships. One of the questions that people started asking is, are there life patterns that generate new patterns? Again, the 1970s, this was Bill Gosper's team again, they discovered something remarkable. They discovered a pattern which became known as the Gosper glider gun. It's basically a stable configuration, and I think every 27 generations, it repeats itself and it emits a glider. This continuous stream of gliders being spun out across the grid. They discovered another pattern around the same time, much simpler pattern, a thing called the Eater. It's a stable pattern that consumes gliders. It destroys them. And this is where things get really, really interesting. Because now we have a signal generator, and we have something that can cancel signals. We have truth and false. We have 1 and 0. And if we have true and false, we can create logic gates. Take a look at this. This is an AND gate implemented in the Game of Life. Now we're going to start this thing running. These A and B here, these are our inputs, and A and B here, this is our output. Now we're going to remove one of these eaters from the configuration, and we're going to run the pattern again. Our input A is now true. There is signal flowing through that, but our output is still false. We're going to flip our inputs. This time, we're going to take out the eater so that B becomes true. We feed the signal through, our output is still false. Now we are going to set both of our inputs to true. A is true, B is true. And when we run our circuit, our output is true. We've created an AND gate using the Game of Life. Now, if we can create logic gates like AND gates, we can create circuits. And if we can create circuits, we can create processors. And if we can create processors, we can create computers. And if we can create computers, we can run programs, including this program that you might have heard about not long ago. It's this wonderful program called Conway's Game of Life. It's a cellular automaton based on these 4 very simple rules. Take a look at this. Now, Conway's game of life is just one of a whole family of mathematical systems that start from very, very simple rules, simple inputs, and they go on to exhibit incredibly complex output behavior. You've probably heard, this kind of study of these kinds of systems became known as chaos theory. The example you've probably heard of is something they call the butterfly effect, that a system can be so sensitive to its initial inputs that, folklore has it, if a butterfly flaps its wings in Mexico City today, next week Tokyo gets sunshine instead of hurricanes or something. Now, there's a whole family of mathematics that was studied, around this idea of complex behavior originating from simple systems. Let's take a look at an example here. Say we've got a grid here, and we're going to draw a square on it, which is 2 by 2. What is the area of that square? It's 4. Now we're going to draw another square there. This is -2 by -2. What is the area of that square? 4. Okay. So if 2 times 2 is 4 and -2 times -2 is also 4, what can we multiply by itself to get -4? Or -3 or -2? Is there any number we can multiply by itself and get a negative result? Now, the answer is no. No such number exists in nature, which is where, physics and engineering goes, well, fine, we've proved it can't exist, no problem. But mathematics goes, here, hold my chalk, let's see what we can do with this. And so we invented this number called I. I stands for imaginary. Now, I is defined to be the square root of -1. We just turned around and we went, well, yeah, this is it, it's I. And anytime you get 2 of these multiplied together, the answer's negative. Those are the rules. Let's go around and play with it. And what gets really interesting is when you start combining these imaginary numbers with real numbers, the numbers we all know about, 1, 2, 3, 4, 5, you get what are called complex numbers. Now, this is an example of a complex number plotted on something called an Argand diagram. So the real numbers are going left to right here, and the imaginary numbers are going top to bottom. And so this point we've plotted here, 0.8 plus 1.2i, this is a complex number. Now, complex numbers are like project plans. They have a part that is real, and they have a part that is imaginary, and they make it very, very difficult to predict what is going to happen next. Now, what we are going to do is we're going to do arithmetic with these complex numbers. And this is pretty straightforward. If anyone did kind of, mathematics in high school and stuff, it's basically the same. We have this number, 0.8 plus 1.2i, and we want to square it, multiply it by itself. So we're going to expand these brackets out, and it's just regular arithmetic, except anytime 2 i's multiply together, the answer is negative. You got that? So we got 0.8 plus 1.2i, all multiplied. We're going to expand those brackets out. Now, you see here, we add together the bit in the middle, we got this 1.2i, those things square, we get 1.44 coming out there as a real number, minus 1.44. The whole thing simplifies down and we get a result coming out the other end. Now, like I said, for a long time mathematics was concerned with studying and solving equations, solving problems. A lot of these systems we're talking about in this talk are not about solving problems. They're about studying the way a system behaves as you iterate it. Let's look at some very, very simple functional systems. So here we have an equation or a function that maps x goes to x plus 1. So 0 goes to 1, 1 plus 1 goes to 2, 2 plus 1 goes to 3. And you can see kind of very, very quickly how this is just going to keep repeating and repeating. And you can intuitively predict what that function is going to do over any number of iterations. Let's take another one down here. This time we're going to map the number x onto 2 minus x. So we're going to start with 0. 2 minus 0 is 2. 2 minus 2 is 0. 2 minus 0 is 2. 2 minus 2 is 0. It just loops round and round and round. Now, we're going to take a number here on our complex plane, and we are going to map this number, z, onto z squared. We're just going to square the input every time we go around. So we're going to take 0.7 plus 0.8i. We're going to square it, and it moves over here. We square it again, it moves over here. We're going to square it again, it moves over here, and boom, it's gone. It's disappeared off our grid and gone off to infinity. But now, we are going to take a very, very subtly different number, one almost the same, but not quite the same as our initial input. And we're going to square that a bunch of times and see what happens. So 0.6 plus 0.8i, first it goes to here, then it goes to here, then it goes to here, then it goes to here. Now, our last one, after 5 generations, it went off to infinity. This one here, is just going to start sort of bouncing around the grid. And it stays fairly tightly bounded. And at this point, it suddenly goes into this weird, almost circular orbit. Now, points that are almost directly adjacent to each other on this grid exhibit dramatically different output behavior. Each of these different lines here, these starting points are almost adjacent. We've run them through this iteration and seen what they've done. The blue one disappears off to infinity. The green one vanishes like it's going to infinity, and then it comes back from the other side of the grid. The red one is stable. It stays in an orbit. The purple one loops round and round and round. Now, the first person to really study the behavior of this kind of mathematics, this iteration of complex functions. Actually, the first people to study it were two French mathematicians in 1910, 1915, Gaston Julier and Pierre Fatou. And they won a medal for their publication about it, but they were limited to working with pens and paper. You know, it would take them a whole afternoon to iterate one of these systems. And so they didn't really understand, they couldn't visualize the significance of what they found. The first person to really do that was this guy. This is Benoit Mandelbrot. By the way, a detail on pronunciation. This is Benoit Mandelbrot, and the thing he discovered is known as the Mandelbrot set by everybody. So Mandelbrot is his name. He discovered the Mandelbrot set. Everyone calls that the Mandelbrot set. My pronunciation's going to slip up. So Benoit Mandelbrot, he was a Polish mathematician whose family, he left Poland, moved to France, and then he spent most of his career working in the United States. He had an awesome job. What Mandelbrot did, he taught mathematics at Harvard, and when he got bored, he would go to IBM and he would play on their computers. And IBM had computers in those days. Most of the world didn't. This is 1960s, early 1970s. And so Mandelbrot had this wonderful balance of kind of pure mathematics and academia and industrial computing and computer innovation. And he was obsessed with the study of the mathematics of nature. He had this very, very famous quote: "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." And he stumbled across this work by Gaston Julier and Pierre Fatou, but he had something they didn't have, because he didn't have to work with graph paper. He could use the IBM computers to understand the behavior of these systems. Now, Mandelbrot's great discovery was this formula. Z goes to z squared plus c, where c is the number you started with. So you take some point on the plane, and you square it, and you add it. And then you square it, and you add the number you started with. And you square it, and you add the number you started with. And what he effectively did was to look at each one of the numbers on this grid and say, after a certain number, say 200 of these iterations, is that number still finite, or has it tended towards infinity? Now, each one of these points on the grid, if it's still finite after 200, we color it in. We say that number is inside our set. If it has tended off to infinity, we leave it blank. We say it's outside the set. And this is exactly how Benoit Mandelbrot and his team became the first people ever to see this. This is a photograph of their original printout of the first ever rendition of the Mandelbrot set from 1970. Now, we quickly developed better computers. We developed faster computers. We developed color displays. We developed better ways of visualizing the behavior of this mathematics. We came up with the bright idea of, what if we color code the points? We say, okay, if it stays in the set, if it never goes to infinity, we're going to keep it black. If it disappears immediately, we'll color it bright blue. If it takes a little bit more time, dark blue. If it takes a long time and eventually goes off to infinity, we'll color it in red. And so we get graph renditions that look like this. And we start seeing these complex, patterns of colors around the fringes of the set here. Remember, the faster it goes away, blue means it disappeared almost immediately, purple means a little bit longer, red means it was very slow, black means we stopped looking, still finite. And when you render this on a modern high-definition color display, you get this, the Mandelbrot set. Now, like I said, technically the Mandelbrot set is the black area in the middle. But, this sort of weird sideways shape, it's a classical shape in mathematics. It's become famous in its own right. And the remarkable thing about it is the level of detail in this shape from z equals z squared plus c is infinite, literally infinite. We're going to take a Mandelbrot set here, and we are going to start zooming in on that set. Now, as the shape is growing here, I'm going to decide that at this point round about now, we're going to call that 1. That's 1 times magnification. So we're going to keep zooming in and in and in and in. And by the time we get to about here, it's 10 times magnification. The original set is now probably larger than the building that you're sitting in. And we're going to keep zooming in some more around about here. That's 20 times. The original set is probably larger than the city in which you are sitting right now. And we can keep zooming in and keep zooming in. That original set that we started with, around about this point, is larger than most countries. Around about this point here, the original set is now larger than Europe at this scale. And we can keep zooming in. Now, I'm going to slow down here, just because this is a good point to stop and look at the scenery and notice one of the astonishing things. This is self-similarity. There are these little pockets inside the Mandelbrot set. They are not the same. They don't repeat. The detail is infinite and it never repeats. But there is self-similarity at an infinite number of scales buried inside this shape. It's astonishing. And all from this one formula, z goes to z squared plus c. Now, the mathematics is simple. But in order for us to see this shape, we had to invent complex numbers, imaginary numbers, complex arithmetic. We had to invent computers. And remember, a modern CPU processor is basically a rock that we filled with lightning until it learned how to think. We invented programming languages, we invented color displays, we invented all this advanced mathematics and technology that allowed us to discover. This was not invented, we found this. This was already here, woven into the information theory that's the fabric of our universe. Now, some people have called the Mandelbrot set the thumbprint of God. I'm not a very spiritual man, but I do play a lot of computer games. And one of the things that I love about games is when you go off on some crazy side quest, or, you're exploring a room that maybe isn't really part of the main story, and you find something that's been put there. You find an Easter egg that says you're on the right track. You were supposed to be here. It's going to be okay. And sometimes I wonder if the Mandelbrot set is maybe a little bit like that. Now, here in 2020, there's kind of no limit to what we can put on computer screens. In the early 1980s, 1982, we had the movie Tron, which was the first kind of full-length motion picture with completely computer-generated scenes incorporated into the film. Tron did not win an Academy Award because the Academy at that time thought that using computers to make films was cheating. They eventually relented. Tron won a Lifetime Achievement Award. We had Luxo Jr. in about 1986, the first completely computer-generated film. We had Jurassic Park in 1994, computer-generated dinosaurs interacting on screen with human actors, making these dinosaurs believable in a way we'd never seen before. A few years ago, we had this guy appear on our cinema screens. Now, you can debate, who is this? Because this is either a digital copy of the dead human actor, Peter Cushing, or this is a digital copy of the fictional character, Grand Moff Tarkin. Now, we're not quite sure which one it is. Lucasfilm's lawyers are working this out as we speak. But we've hit a point now where, we can bring pretty much anything you can imagine to life on a computer screen. We can ask questions like, hey, what would it be like if they remade Friends, but they got Nicolas Cage to play all the parts? Now, the reason we can create great works of art like that one there is we've studied the way human brains learn. Well, there's things that human beings are really, really good at. We are brilliantly good at recognizing patterns and faces. You ever lie on your back in a field on a sunny day and you watch these clouds kind of drifting overhead and you're like, that one looks like a rabbit, and that one looks like a cat, and that one looks like an airplane. Oh no, that is an airplane, hang on. And what your brain is doing is it's running pattern recognition algorithms. And we have come up with ways of creating computer vision and machine learning systems that can kind of mimic this behavior. The classic one is something called a convolutional neural network. Now, we don't know exactly how these systems work because we didn't so much program them as wire together a bunch of stuff and then let it learn by giving it input. So we take a neural network and we say, here's a bunch of pictures. These pictures are cats. These pictures are dogs. Please figure out the difference between cats and dogs. And it runs a whole bunch of logic. And eventually you come up with a computer that says, yep, I can recognize cats now. Now, it might not sound that difficult. So let's say you want to tell the difference between, a puppy and a muffin. Doesn't sound that hard, right? Okay. But what gets really interesting is when we take that neural network, we've trained this neural network to identify dogs, to look for features of dogs, ears and noses and eyes and all the things that we humans use to say that's a dog, that's a dog, that's a dog. What if we take our dog detector and we flip it around, we wire it in backwards and we turn it into a dog amplifier? And then we give it a picture which doesn't contain any dogs, and we say, find the dogs and enhance the dog features. And the computer goes, this is a terrible idea. And we go, do the thing. And the computer goes, all right, you asked for it. And we go, increase the power. And the computer goes, I really don't think. We go, increase the power, and it goes, all right, you asked for it. And we end up with images like these. Now, this technique is known as deep dreaming. It came out of a project called Deep Dream that took place at Google back in 2015. And I love this. This to me is a completely new kind of art. It's a new kind of image that elicits an emotional response in the people who look at it, because it's kind of freaky, isn't it? It's weird and it's unsettling. And you're looking at this picture and your brain keeps going, that's a dog, no, that's not, that's not. And this bit of our brains that's good at recognizing dogs is kind of getting fooled by this the whole time. Now, this kind of stuff is fantastic. I love the opportunities that modern computers and modern technology have for creating new kinds of art just because it's cool. Putting Nicolas Cage's face in everything and running a dog amplifier on a picture full of jellyfish and all these kinds of things. But let's stop talking about using computers to create art now. Let's start talking about the idea of computer programming, of software, as an art form in its own right. Now, one of the most famous books in computer programming history is this, The Art of Computer Programming by Donald Knuth. And, we have these ongoing discussions. What is programming? Is programming art? Is it science? Is it engineering? Is it typing? But I'm sure all of you, anyone who's ever worked on a team or worked on open source, will at some point have been asked to review some code. And you'll have looked at that code and you'll have been like, I'm not sure what this is. It's not engineering. It's not science. I'm not sure that I dignify it by calling it art. I really don't know what to make of it. Well, the good news is there is a safe space for this kind of code, and it is obfuscated coding contests. Here are the goals of the International Obfuscated C Code Contest. To write the most obscure or obfuscated C program. To show the importance of programming style in an ironic way. To stress C compilers with unusual code. To illustrate some of the subtleties of the C language. To provide a safe forum for poor C code. Now, I'm sure some of you watching this today are C programmers, so I'm going to show you some code. We're going to do a little code review exercise. What do you think this does? Now, I'm not much of a C programmer, so when I need to review some code to see what it does, first thing I do is I run it. Let's run this and see what it does. We'll run it through make, we're going to run the program, and there we go. It's Flappy Bird running in a Unix terminal. And it is no easier than Flappy Bird running on any other kind of terminal. It is still fiendishly hard. Let's have a look at another one. So here's a snippet. I don't want to show you the whole thing yet. This is a snippet of some C code. Now, if someone on your team said, do you want to review this code? You'd have questions, right? Maybe some constructive feedback about things like a brace style and new lines and those kinds of things. But when we zoom out and we look at the whole program, this is a Mandelbrot set generator written in C, shaped like a Mandelbrot set. I think that's rather beautiful and delightful. Let's take a look at another one. One of the goals of obfuscated code is to make things small. See how much you can fit into a tiny amount of space. This is 1 kilobyte of JavaScript. And if you copy and paste this into a web browser and you run it, it will play chess. It won't draw a chessboard, it will play chess. It will play a game of chess. It is better at playing chess than that Amstrad computer that I had when I was a kid. All of this is done in less than a kilobyte of JavaScript. This is a guy by a guy called Oscar Toledo G, who keeps winning these obfuscated coding contests. He's an absolute genius when it comes to writing weird computer programs. Now, in 1994, somebody called Simon Rysinkevich. Now, in 1994, somebody called Simon Rysinkevich submitted this to the International Obfuscated C Coding Contest. This is an empty file, and it came with instructions that if you run it in a certain C compiler that was around in 1994, it would produce a valid program that created no output. And so Rysinkevich argued that this was a Quine. It's a program that produces its own source code. Now, he won a special prize, a special recognition, and they changed the rules of the Obfuscated C Code contest to say that all of your programs now had to include at least one character of input. But this gets us onto this whole wonderful idea of Quines, programs that print their own source code. They are named for a philosopher called William Ormond von Quine, who wrote about statements that refer to themselves, and were kind of popularized in this book, Gödel, Escher, and Bach by Douglas Hofstadter. Now, how hard can it be to write a program that prints its own source code? It's not. Can it be that difficult? And you're not allowed just to read it off disk. That's cheating. So we're going to have a go. This is C#, and I'm going to try and write a C# program here that prints its own source. So we got a class program, static void main. Yeah, makes sense so far. Now the first thing we need to do is we need to print the console.writeLine, the class program, and the closing brace. And then we need to console.writeLine the static void main and the closing brace. But now we need to console writeline the console writeline, and very, very quickly you'll find yourself just getting tangled up in this kind of infinite recursion nested print statements all the way down. To write Quines, you need to exploit the loopholes that exist in the languages you're working in. What if we do this? We're going to take a multi-line format string, which is a legitimate thing in C#, and we're going to say this is class program static void main. And then we're going to say var s equals, then we're going to put in three placeholders, 0, 1, and 0, and then a system console writeline. We've got a literal char34 in there. We'll look in a second at why that's important. And then we're going to take that format string, and we're going to feed it back into itself, so that it basically prints a copy of itself wrapped around itself. So when we run this program, it's going to print its own source code. The char34 there is necessary because we need to inject a quote into this thing without closing the literal string. And this works. This is a C# program that prints its own source code. Now, all languages have different strengths and weaknesses and loopholes that we can exploit to pull off these kinds of tricks. In JavaScript, all functions have a toString built into them. So any function f is just f.toString, and that'll give you its own source code. In ECMAScript 6, this is a Quine. Now, I didn't believe this, so I opened it up and I ran it, and sure enough, this statement produces a string containing its own source code. Now, you can do Quines in all sorts of languages, and a while back I saw something I thought was absolutely beautiful. There's a guy called Leon Bambrick who created a Quine in HTML. So inspired by him, I want to walk you through the process of creating an HTML Quine. So here we have some HTML source code, and when we look at it in a browser, it looks like this. Now we're going to start breaking some rules. First of all, we're going to add some style sheets, some inline CSS, and we're going to say everything, including things you don't normally see, should be displayed as a block in a monospaced font. Switch back over here. Look at that. The first line of this output, we can see our own CSS rules now. Now we're going to start using some pseudo selectors. We're going to say, well, before the HTML element, put HTML, and afterwards put /HTML. /HTML's here, it's just it doesn't know where to put it, so it's off the bottom of the screen. It's after the end of the entire document. We're going to start repeating this pattern. We're going to put a little bit more stuff around our style sheet now, so it begins and ends. Now you'll notice there we got style after ///style. That's because if we put /style, the parser is going to choke, and it's going to hand the rest of it, it's going to think the CSS is finished and hand it back to the HTML parser. That's not going to work, so we need to escape it. And there we go. We've now got our style and /style coming out in our page code. We're going to add a bunch more of these. There's no way of programmatically generating them, but we can put them in without too much difficulty. Now, we've got this link here. We want to include the web address that that link is going to, so we can put the attribute inside the pseudocode using a before pseudo element, using CSS, and bang, there we go. Inspired by, and there is the link. I'm going to add one more rule to this. I'm just going to say HTML 16 pixel margin and make the height 1%. So it's just going to kind of squash the whole thing down like this. Let's refresh that. And there we go. We have a web page that prints its own source code. Completely useless, but I think it's kind of beautiful, don't you? Right. Let's have a look at some more code. Who wants to tell me what language this program here is written in? We got a hash include at the top there, yeah, and you know, some standard io.h. Let's apply some syntax highlighting. Let's say this is in C. There we go. Yep. It's not the most readable C that I've ever seen, but it looks like a valid C program. But what if we take the same source code and we apply syntax highlighting in Ruby? And then we highlight the string literals. That's a valid Ruby program. So which is it? C, Ruby? Let's try running it through some compilers and see what results we get out of this. So I'm going to run this thing through just to show you. This is polyquine.c. There's a clue in the name there. There it is. Now I'm going to run that thing through GCC and I'm going to run the output. I get a warning, but hey, what the hell? We took the safety off a long time ago. I run the output file and it prints its own source code. And now I'm going to run that same program and I'm going to go and I'm going to run it through the Ruby interpreter. So Ruby on polyquine.c, it prints its own source code. Let's try another one. What if we run the same source code program through Python? And there it is, it prints its own source code. What if we run it through Perl, which I had to install on my laptop just to do this demo? There it is. It prints its own source code. This one program is syntactically valid and prints its own source in C, Perl, Python, Ruby, and C++ if you can find a compiler that doesn't complain about main not having a return type. Now, this is a polyquine. It's a program that's valid in more than one language. It prints its own source code in all of them. And if you think that's cool, check this thing out. Now, who wants to tell me what programming language this is written in? Well, let's have a look. We've got system.console over here, which is kind of like a .NET kind of a thing, right? We got XML, XSL namespace here, so maybe there's some XSLT going on here. We've got for each and a console.log, which looks kind of JavaScripty, right? We've got an Ada text IO procedure. Now, I'm not an Ada developer, but you know, maybe it's safe to assume that if it says Ada, it's an Ada program. We've got begin in all block capitals, which is COBOL, or maybe SQL Server. It's certainly mainframe 1970s type language. And then we've got Act 1, Scene 1, Enter Ajax over here, which doesn't even look like a computer program at all. It looks like a play, right? This is something called the Ouroboros Quine, written by Yosuke Endo, who's one of the Ruby language core contributors. It is a Ruby program that produces a Rust program, that produces a Scala program, that produces a Scheme program that goes through 128 languages, and eventually you end up with a RC program that produces a Rex program that produces the original Ruby program back again. Now, one, this is astonishing, you know, an astonishing feat of just brilliant, weird computer programming as art. Two, have a look at the source code for this, for the Ouroboros Quine. That's it. That's the entire source code. And if we zoom in, have a look at how it ends, because at the end of this code, you'll notice buffer for future bug fixes, 4 or 5 lines of padding space in there, just in case they find a problem with it that needs to be, they need to go in and they need to sort out and fix later. And the absolute best thing, about this, the Ouroboros Quine program, is that all 128 of those languages are available on Aptitude. You can go onto an Ubuntu Linux machine and you can type apt-get install Ruby, Rex, Sed, Shakespeare, all of those languages, which means that there is a continuous integration step for all of those languages built using GitHub Actions, that every time a change gets committed, it runs it through all 128 of those and verifies that you get the original result back out of it. Isn't that brilliant? Now let's backtrack a little. You remember that program there, Act 1, Scene 1, Enter Ajax? That was a programming language called Shakespeare. Shakespeare is what is called an esoteric language, an ESOLang. It is a computer programming language that is designed to let you write programs that are fun, weird, unusual, esoteric. In this case, Shakespeare was specifically designed to let you create computer programs that look like Shakespeare plays. Let's have a look at Hello World written in Shakespeare. So this is the infamous Hello World program. Variables are declared as characters. Romeo, a young man with remarkable patience. Hamlet, the flatterer of Anderson insulting AS. Act 1, Scene 1, so we've now declared scope. We've got function scope here. Enter Hamlet and Romeo introduces those variables in this scope. Now, the way Shakespeare works is variables are incremented by flattering them and decremented by insulting them. So when Hamlet says, "You lying, stupid, fatherless, big, smelly, half-witted coward, you are as stupid as the difference between a handsome, rich, brave hero and thyself, speak your mind," we've put a variable, a value into Romeo, and then speak your mind, Romeo is going to print the letter H. You are as brave as the sum of your fat little stuffed, misused, dusty old rotten codpiece, and a beautiful, fair, warm, peaceful, sunny summer's day. You are as healthy as the difference between the sum of the sweetest, reddest rose and my father and yourself. Speak your mind is going to print E. Hello World takes about 5 pages in Shakespeare, but that's fine. It's influenced by Shakespeare. You know, brevity is not one of the things the language is optimized for. Let's have a look at another example. Who wants to tell me what programming language this is written in? This is the programming language called Whitespace. I'm going to apply some syntax highlighting. In Whitespace, all of the instructions are sequences of spaces and tabs, and everything else is ignored. Everything else is treated as a comment. Whitespace is a brilliant language for hiding programs inside other programs, because most other programs ignore the whitespace and they look at the characters. Whitespace does the exact opposite. Let's have a look at another one. Now this is the Hello World Souffle in the programming language called Chef. Now Chef is designed for creating programs that are also recipes. Now the Hello World Souffle here, have a look at the ingredients we got here. 72 grams of beans, okay, 101 eggs, 108 grams of lard, maybe, 111 cups of oil. This is a very kind of greasy, eggy kind of dish we got going on here. 33 potatoes, 32 zucchinis, and 114 grams of red salmon. Now, this prints Hello World, but you wouldn't want to sit down and eat it. And this is where our next esoteric programmer comes in. It's a chap called Mike Worth. Mike created the Hello World cake with chocolate sauce. He wanted to create a Hello World program in Chef that actually yielded a usable, edible recipe, and he created this. If you run this set of instructions on the Chef interpreter, it prints Hello World. If you run it in your kitchen, you get cake. Chocolate cake you can sit down and eat with a chocolate sauce to pour over the top of it, because apparently it was a little dry. Let's take a look at another example of esoteric languages. Let's have a look at how to square a number in the programming language called Pete, named for Pete Mondrian. This is the source code, because Pete is a graphical programming language. The instruction set is dictated by the hue and the lightness of the colors that exist in this grid. Whenever the function pointer, the cursor, crosses from one color to another, that color boundary is an instruction. This is the set of colors that are supported by the language, and this is how squaring a number actually works. The function pointer starts up here in the top left-hand corner. When we cross from light blue into dark green, that is input. Input prompt the user to input a number. When we hit black, we change direction. When we cross from green into red, H4 duplicate whatever number is on the top of the stack. We now have 2 of the same number. We cross from red into yellow, that's a multiply. Pop 2 numbers off the stack, multiply them, put the result back on the stack. Yellow into red, output. Print whatever's on the top of the stack. Red over white, that's a no operation. When we hit blue, we hit the edge of the grid, we turn right. We follow blue as far as we can until we end up with black on all sides, and that means halt. The program has completed. Now, the wonderful thing about Pete, the thing I love about it, is you could print that Pete program out and hang it on the wall, and nobody would know that they were looking at a computer program. They just think you like kind of slightly weird, expressionist art. Here is Hello World implemented in Pete. Isn't that, beautiful? Now, we've talked about software being used to create art. We've talked about software as art. We've talked about entire programming languages, which are art in their own right. But now I want to talk about something different, because when you go to conferences, quite often there will be talks that involve live demos, kind of code as performance. And there's always an element of excitement in a live demo, because there's that kind of risk. What if it doesn't work? Is it going to work? What if something goes wrong? Someone is live coding on stage and maybe it'll succeed or maybe it'll fail. Now, we don't like failure as software engineers generally, you know. We have this word. Have any of you ever heard of a snowflake server? It's like that one box that was set up with Windows 2003 and just the right combination of patches and ActiveX objects. And no one can touch it. Don't install Windows Update on it. It's unique. It's a fragile, special snowflake of a server, and if anyone ever breaks it, we don't know how we're going to make another one. And this is kind of a derogatory term, because in software we want everything to be reproducible. We want to automate everything and script everything. But if you go out in a snowstorm and you pick one snowflake and you let it melt on your hand, every snowflake is unique. By watching that flake melt, you've just been part of an experience that wasn't recorded, can't be shared with anybody. You were literally part of something unique that will never, ever be repeated. And this brings me on to the idea of software as performance. Software as a live performance. Now, this guy up here sat underneath the big screen. This is Sam Aaron. And Sam is the creator of a programming language called SonicPy. SonicPy Now, this guy here sat up underneath the big screen. This is Sam Aaron. And Sam is the creator of a programming language called SonicPy. SonicPy is unique. SonicPy is a programming language for music. This is I want to give you a very quick run through of what SonicPy actually does, of how SonicPy works. So, for starters, simplest instruction, the kind of hello world in SonicPy is you just go and you say play A3. And we get a note. Okay? Now, SonicPy will run all of your instructions simultaneously unless you tell it not to. Imagine if JavaScript did that. If you want notes to play one after another, you have to introduce delays. Okay? Now, what gets really interesting with SonicPy is when we start introducing the idea of loops. We're going to put in this loop here. Now that's not terribly exciting, you know. It's a bit of a slow, pedestrian kind of loop, so let's crank up the tempo a bit. It's getting more interesting. We're going to change the synthesizer noise that we're using. I'm going to use something called Texels. Now we're getting somewhere. This is starting to sound interesting. But what makes SonicPy really, really cool is when we introduce the concept of something called a live loop. Because SonicPy will let you rewrite and modify your code while it is running without changing anything. So we're going to drop this loop in here. And then I'm going to put in another loop underneath called symbols, which are going to synchronize with that main loop there. And I'm going to say 15 times, play a closed symbol and wait, and then play the open symbol. And we can just drop that in. Our program doesn't interrupt. We don't need to restart anything. And now we've got the symbol track. I'm going to paste in a drum loop that I prepared earlier. I'm going to drop that in underneath. It's getting interesting, right? Now, our main loop there, our baseline, our Texels synthesizer, I'm going to put in a thing that says, count the notes, and if the note is divisible by 3, I want you to play a different note. And I'm going to put in another test. If the note is divisible by 5, play a different note. And finally, you can probably see where this is going. If the note is divisible by 15, play another note. This is called the Fizz Buzz Riff. And listen to that, because we're going to be seeing that again before the end of the talk. But it's Fizz Buzz implemented by coding in real time in a musical programming language. We're not printing anything onto screens. All the output from that is music, live music. It is coding as art, as performance. Sonic Pi is fantastic. It runs on Raspberry Pi, so you can get a computer for like, 10 euros, plug it into your TV and start playing around with that. It's used to teach kids programming, but it's also used live on stage by bands and DJs all over the world to do live algoraves, algorithmic music, and algorithmic performance. So, we've talked about all kinds of cool stuff that other people have done. Now, for the last part of the talk, I want to tell you about something I did. Now, you're probably familiar with this idea we have in IT of Rockstar developers, because you've seen the job advertisements, right? Wanted, Rockstar developer, Rockstar Java developer, Rockstar JavaScript. So we've talked a bunch about all kinds of cool stuff that other people have done. But in the last part of the talk, I want to tell you about something I did. Now, you're probably familiar with this idea that we have in software of the Rockstar developer, right? Because you've seen the job adverts. Front-end Rockstar wanted, Rockstar senior front-end developer, Rockstar JavaScript programmer. Are you a Rockstar senior Java software developer? And then somebody, Paul Stovell, put this on Twitter. To really confuse recruiters, someone should make a programming language called Rockstar. And I had this experience. I thought, this is it. This is my purpose. This is why I was put here. Because when I wasn't wasting my childhood and my teenage years getting computers to do funny things with pictures, I was listening to music by these kinds of fine people. And it was obvious what the world needed. We needed a programming language where you could write programs that were also bad 1980s rock and hair metal songs. And so Rockstar was born. A dynamically typed Turing-complete programming language designed for creating computer programs that are also song lyrics, heavily influenced by the lyrical conventions of 1980s hard rock and power ballads. Now, every programming language starts with Hello World. I decided, now it's worth noting here, Rockstar was invented in a bar as a joke. This is not the ideal time and place to design programming languages, and some of that will become apparent shortly. But I sat in this bar, I had a couple of beers, I had my laptop, and I was just kind of riffing on fun ideas for a parody language specification. I said, all right, what if Hello World, just say Hello World? That's nice and easy, isn't it? But also scream Hello World, or maybe whisper or shout, because, this is rock and roll. You want to be able to express yourself. Programming languages need variables. Programming languages need assignment. Now, most languages kind of int x equals 5, my underscore string, the message. You ever have one of those arguments, like, upwards of 3 hours about whether to use Pascal case or camel case or kebab case or chase or this case or that case or that case? Now, first of all, Rockstar is dynamically typed. We don't need int, var, var. We also don't need semicolons because JavaScript doesn't care, Python doesn't want them, Ruby doesn't want them. We can live without them. This is fine. That equal sign there isn't terribly lyrical. Let's just replace it with is. X equals 5? Well, no, X is 5. That works. Now, the underscore in the Pascal case, I saw Douglas Crockford give a talk a few years ago where he said all these arguments we have about Pascal case and underscores and camel case, what we really want is variable names with spaces in them. Now, when you're inventing a programming language in a bar, you can do anything you like, right? Boom! Variable names with spaces in them. Now, this wasn't a complete, there was some thought went into this. I decided there were going to be 3 different kinds of variables in Rockstar. There are simple variables, foo, bar, baz, just like in most dynamically typed languages. There are common variables. My heart, an ocean, your dream, a kiss, the night, starting with one of these prefixes. And anything with capital letters, Dr. Feelgood, Black Betty, Billie Jean, these were proper variables. As long as you keep starting with capitals, you can just chain them together. Now, quite often in programming, we need to initialize variables with numeric values. And that's kind of hard to do in rock and roll. There's only so many songs you can write about someone's phone number. So I thought, fizz is 3, buzz is 5, the limit is 100. Because we got to write fizzbuzz, right? Otherwise, how can you interview Rockstar developers? I thought, we got to be able to initialize these what if. We take the lengths of the words on the line, modulo 10, and treat those as the digits in a decimal number. So ice, 3. Dying, 1, 2, 3, 4, 5. A love-struck lady killer 100. This is how you initialize 3, 5, and 100. We're just getting warmed up here. In C#, you want to initialize a decimal of pi, 3.141, blah, 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 blah. In JavaScript, var pi equals 3.14159, and after this you're in floating point arithmetic, so you're probably not getting it back exactly anyway. In Rockstar, you can use poetic literals with decimal places. My heart was ice, period. A life unfulfilled, waking everybody up, taking booze and pills. 3.14159265335. We've got numbers. We need to do arithmetic. We need to be able to add things. Now, in English, we have all these kind of ways of talking about stuff. Well, like, how much is it? Oh, the total is the price with the tax, right? It's the total without the tax. That's the price. We say the quantity of the product. We talk about distance over time, these kinds of things. So with, without, of, over, this gives us some lovely capacity to express ourselves in arithmetic. We can talk about a girl with a dream, a man without a face, the wings of the night, a whisper over the water. We need to be able to do comparison. Equals is. Your love is a lie. True or false? Well, is it? The whiskey ain't the answer. True or false? My heart is stronger than steel. My soul is weaker than water. My will is as strong as a lion. Your lies are as low as a snake. We need to be able to write functions. Now, functions in most languages use brackets and braces and all kinds of complex, the sort of punctuation you don't really get very often in rock and roll. I wanted to do it all using words. So I thought, all right, well, a function takes arguments. You have a modulus function, it takes a number and a divisor. Now, modulus we can do with a test and a loop where we just repeatedly subtract something until we end up with a remainder. So while a number is as high as a divisor, put a number without a divisor into a number, give back a number. You see the blank line there? That's how you terminate loops in Rockstar. So this is minimalist Rockstar. You can write the same thing as midnight takes your heart and your soul. And while your heart is as high as your soul, put your heart without your soul into your heart and give back your heart. I figure we're done. This, a couple of beers in, I have a parody specification, I can write fizzbuzz in it, I stick it up on GitHub, I put it on Twitter, I go back to my hotel, I go to bed. The internet gets a little bit excited about this. Overnight it got 2,000 stars on GitHub. When I got up the next day and checked social media, this thing was everywhere. There was stuff on Hacker News, there was stuff on Boing Boing, there was people on Reddit saying, Reddit was saying nice things about this. I don't know if you hang out on Reddit, it is unusual for Reddit to say nice things. Then something happened that I absolutely did not expect. A couple of days later I get an email from Classic Rock Magazine, which is a real, rock and roll magazine that interviews, Metallica and Guns N' Roses, people like that, emailed me saying, what is this Rockstar thing we keep hearing about? So they did an article. I made it in Classic Rock Magazine for inventing a joke programming language in a bar. And it's just getting warmed up. Because a couple of days after that, people started filing issues on my parody specification. And they started saying things like, some of it was syntax highlighting, but some of it was there's ambiguities in the language spec. And I was like, why do you care? And they said, because my compiler has undefined behavior. I said, you're what? They said, yeah, I built a Rockstar compiler in Scala over the weekend. Well, of course you did, And someone else had built one in Rust, and someone had built a Rockstar to Python transpiler. And this was, way beyond anything I thought was ever going to happen. And I kept thinking that it would be it. Like, that was the, end of the fun, and the buzz was going to die out. And it just kind of kept going, It's like the enthusiasm for this project rolled on and on and on. And after about 4 months, it was January the 1st of 2019, it made the front page of Reddit again. Another kind of bunch of developers found it. And people started saying, Dylan Beattie, the creator of Rockstar. Now, I kind of like the way that sounds, but I also didn't feel like I'd really done enough to deserve it. And so I figured the only logical solution to this was to build my own Rockstar interpreter in JavaScript, because why not? Well, actually, I'll tell you why in JavaScript. I knuckled down, I read a whole bunch of programming language design, I learned about parsing expression grammars, dug out my old university books about recursive descent parsers, and I created a project called Satriani, which is a JavaScript interpreter for Rockstar. The reason why I did it in JavaScript is I wanted it to run in a web browser. So anybody, anywhere in the world, with a phone or a laptop or a desktop, can go to this website, codewithrockstar.com, and they can paste their code in there and they can click run. And as soon as you've done that, you are a Rockstar developer. And you can go and get all those sweet jobs on LinkedIn. Now, you see that logo in the corner of the website there? I wanted Rockstar to have some kind of fun rock and roll kind of, 80s over-the-top glam metal styling about it. And I was looking around for influences, for something I could borrow, and I looked at all these band logos, and none of them was quite what I was looking for, until somebody suggested, have you thought about Microsoft Consumer Products 1980 to 1982? And it was perfect. And they're not using that logo type anymore. They haven't for a long time. So I thought, let's all be, sustainable here. I'm going to recycle it. So thank you very much, Microsoft, for, I didn't quite kind of ask, but they haven't said anything. So thank you, Microsoft, for letting me recycle the typography from your 1980s logo. You're all Rockstar developers out there. Now, I have launched the Rockstar certification program. Unfortunately, if you're watching this talk live on the live stream, you will not be able to come up at the end and get any stickers because we are giving out stickers. This is the world's most prestigious developer certification program. The certificates are all self-adhesive, so you can stick them on your laptop. So if you catch me out on the road at a meetup or a conference somewhere, come and say hi. Get yourself a certified Rockstar developer sticker. Let's get out there and apply for all those jobs on LinkedIn until people stop claiming that Rockstar developer is any kind of job title. And finally, I'd like to end this talk by asking for your help with a little experiment. You saw the Mondrian, the Pete Mondrian Hello World program that looks like real art. And you saw the chef Hello World chocolate cake that makes a real cake. The test for whether Rockstar as a project was successful is, can you write a Rockstar program that's also a real song? So I'm going to perform it for you now, and I want you to take a listen to this and tell me, do you think it worked?
As high as your soul, put your heart without your soul into your heart. Give back your heart. Struck a lady killer. My world is nothing. Fire is ice, hate is water, till my world is desire. Build my world up. If midnight taking my world, fire is nothing. nothing. Shout, fizz, buzz, take it to the top. At midnight, taking my world, fire is nothing. Shout, fizz, take it to the top. If midnight taking my world, hate is nothing. Say buzz, take it to the top. Whisper my world.
Thank you, Internet. It's been a lot of fun. See you out there somewhere.